Hi everyone, welcome back to homework 4. So this is going to be the video for part 2. So what we're looking at here is we want to implement functions for calculating the dew and bubble temperature using NRTL activity coefficient model and apply these to calculate the dew and bubble temperature of equimolar mixtures of methanol, ethanol, and water at this pressure given. And then what are the corresponding compositions of the first liquid drop and the first vapor bubble that form? Okay, so we're just gonna jump in right here. I actually just put Raoult's law here. This is gonna help us with the bubble pressure, bubble temperature, right, dew pressure, dew. It'll just help us with everything. Um, so we're actually just gonna get right in. So we want a bubble pressure. So we'll just call it BP for bubble pressure. And we're gonna want our composition and the temperature. And if we look at this right here, basically the partial pressures are equal to the this gamma, which is actually something we calculated already. So it's going to be up here. And we can actually take this, we can actually just pull it right out of this function we already got. So we'll just copy that. So it's going to be equal to that activity coefficient times x, which we can see right there, times the vapor pressure. So we can actually take that from these properties that we did at the beginning. It's properties from CHE4. PVAP at the temperature. And actually we'll just put a T there so we can say whatever temperature we want. And then we're going to have our total pressure equals the sum of the partial pressures. Sum PI. And then we want to return total pressure along with the partial pressures. Well, I guess, well, we're returning the partial pressures divided by the total pressure. And if we call BP, why does that pop up there? Using X and 300. Okay, so we get 0.53, 0.29, 0.16, with a total pressure of 11,413. So this is going to be our bubble pressure. So the pressure, basically at the pressure at the bubble point. So where the first bubble forms. But actually, what we want to find is the bubble temperature, not the bubble pressure. So we're going to go back in. I'm going to keep this up here just for reference, so we can check to see if our bubble temperature is working correctly. So I'm just going to define a new function called bubble temperature. And this is going to be basically the inverse of the bubble pressure. And the way we kind of want to tackle this is we're going to do this bubble pressure thing. And we're basically just going to try temperatures until we get the correct ending pressure that we want. And the way that this is set up, the temperature of the mixture should be in between the boiling points of the highest boiling point and lowest boiling point compounds that we have. So that allows us to have bounds on where our guesses are for the bubble temperature of the mixture. So instead of using a zero solver, we can actually use this thing up here called Brent Q. We're going to use that to basically find our bubble temperature. So first thing, we need the boiling points. So the temperature of boiling is going to be equal to, we're going to take this from properties, so TB and P, so at that pressure. And then from that TB, we want to take the highest and the lowest. So we'll call it T low, T high equals NP dot min TB and NP dot min in NP dot max TB. TB. So I'll take the lowest and the highest. And then what we should have is take a look at Brent Q. So for Brent Q, we're going to need a function to actually use to find the root. And then we're going to need our two bounds. So just keep this Brent Q here. So in order to use Brent Q, we're going to need a function. So we're going to have to define another function. And I'm just going to call it an equivalent function. Just going to use the temperature. And then the way we want this to work, we want this function to basically calculate the boiling pressure, because we want to find the zero of this function. So if I actually take this boiling point function from up here, I should just be able to return that. Return boiling pressure using X and T. And then in order for this to be a zero, we want to subtract pressure, because we want it to equal zero. And then that we should be able to use Brent Q for this now. So equivalent function, T low, T high, and that should put bounds on it. Now actually, something we want to keep in mind, there may be a case where we have a azeotrope where the boiling temperature, or the bubble temperature might be outside the range of the boiling points. So what we can do is we can just give it a small buffer, just in case. Have it look like that, and then we actually just want to return this. Turn Q. Okay, so now if I go ahead and call this BT at X, and I'm going to use a pressure of this right here. Let's see, what is the issue? I think I need to specify which one I want to grab. So 0. Okay, and this tells us that at a composition of equimolar and a pressure of this number right here, which we got from a temperature of 300, it gives us a temperature of 300, which means that this function works correctly. This is this basically just confirms that our bubble temperature and bubble pressure, they both work correctly. Okay, so I'm just going to delete that. We could probably just delete that too. Okay, and I'm going to move on to dew point. So for dew point, the first thing I'm going to do is I'm going to do a simplified version of dew point. So basically without this activity coefficient, just to see how we would set it up. So define dew pressure. This is going to need a Y for mole fractions and a temperature. And then actually the way dew point works and is calculated, we can actually rearrange this if we ignore, of course, this activity coefficient just for a moment. We can actually get it to equal 1 divided by the sum of the mole fractions, so Y, divided by the vapor pressures, so P dot P vap T. And that's actually just the dew pressure. So I'm going to come down here, dP. And just for simplicity's sake, I'm just going to use equimolar for the gas, for the vapor mole fractions. Of course, they're not going to be the same as the liquid, but just for simplicity's sake, we're going to do that. Oh, I guess we should return this. Okay, so we have this 6683.799, blah, blah, blah. And then I'm going to come down here, define dew temperature. And dew temperature is just going to take in the opposite. So instead of Y and T, it's going to be Y and P. And we're basically going to do the exact same thing as we did up here. So I'm just going to go ahead and copy this down. We're going to want to change a few things. So this is going to be dew pressure. And is that it? Dew pressure. This needs to be Y. And I think that should be it. So then we're going to call dt using x and this pressure right here. We're going to be able to check it with that. Let's see, too many. What's the error? Deep. What is the error? Too many indices raise index error. Oh, here we go. dt x and this. Doesn't seem to like this for some reason. I wonder why. No, that didn't fix it. I don't know, I'm just gonna run all this real quick. Oh. Whoa, what happened? Oh, never mind, confusing myself. P is TB, that pressure. Yeah, this should be the same thing. But for some reason, it doesn't like. Maybe there's some weird indentation or something. Oop. Doesn't look like it though, which is odd. Brett Q, equivalent function, T. No, that's... I think I might be confusing myself here. Give me 1 second. Okay, so obviously if I have this x here, we get an answer, but I need this to be y instead. Am I... oh, because... oh, hold on. So this needs to be y. This needs to be dp yt, because that's dp bt, or this is bp xt minus the pressure. Okay, so that's dp. I guess I can see how all these variables can get a little confusing sometimes. Give it a second to try and debug this real quick. Equivalent function. Right, y is not defined. Yes, that makes sense. Yeah, but then when I... what is going on? Equivalent function t... So there's a dp y t 0 minus p. Okay, I'm going to take a second to try and figure out what I did wrong here. I'll be right back. Okay. That took me about 10 seconds. So this 0 here, we actually... I forgot to delete that. We don't need that anymore. Just the way the dew point is set up. So actually when I go ahead and run this, we get... oh, where did it go? 300 degrees, which is... basically what we started with, 300 degrees. So this shows and confirms that our dew pressure and dew temperature equations are working correctly. So I'm going to go ahead and get rid of this real quick. So we have boiling pressure, boiling temperature, dew pressure, dew temperature. Now, one thing we need to keep in mind for the dew pressure, dew temperature, this is technically the, I guess, ideal dew pressure, ideal dew temperature. Because in reality, we need to have this activity coefficient in mind. So what we're going to need to do is do the, basically do the temperature again, but this time with the activity coefficient in mind, which is going to change as the temperature changes. So it's going to be quite a bit more complicated, and we're going to go through that in Python. I'm actually going to cut the video here, and we will go ahead and do that in the next video. So I will see you in the next one.